Alright, let's get started with Lesson 4, Rate Law, Part 1. Now in Part 1, all we're going to do is introduce to you the rate law expression, the basic parts of it, and the basic ideas and concepts of the rate law expression. In Part 2 and 3, we'll get in more into the application and how to use the rate law expression in order to solve problems in the mathematical sense. So, exactly what is the rate law expression? All right. So the rate expression, also known as the rate equation, states in a precise way and how the starting concentrations, and I'm going to highlight that, of all reactants affect the initial rate of a chemical reaction. So the rate expression expresses the rate of a chemical reaction in terms of the concentration of each reactant raised to a specific power. All right? There's a lot there. So we kind of break it down for you. All right? Below here we have a chemical reaction in a symbolic sense. We have reactant A, which is represented by capital A, reactant B, capital B, and product C and D. The lowercase letters are the coefficients in the balanced chemical equation. E is the catalyst in this reaction. Usually, if there is a catalyst present, we put it above the arrow in the reaction to represent that it is a catalyst and not being consumed in the reaction. It's neither a reactant nor is it a product. All right? So the rate expression then for this reaction is represented by the following equation. The rate, and this rate is the initial rate of the reaction, is equal to K. Now K is known as the rate constant, all right? Okay, the rate constant. The rate constant is multiplied by the concentration of A, B, and the catalyst. Now, the brackets that you see here, whenever you see brackets with a reactant or product, or even a catalyst in those brackets, the brackets represent concentration, always, okay? And specifically, the concentration is going to be in moles per liter, or in the IB sense, moles per cubic decimeter. Okay? So we're talking about molarity concentrations is what those brackets mean. Whenever you see brackets around reactants and products, that's what it means is concentration in molarity. All right? So in this case, we're talking about the initial or the starting concentrations. All right, and each of them are going to be raised to some power. Okay, now the power that that we raise the reactant to is known as the order. For, oops, erased that. Okay, the order for that reactant. Okay, and we'll talk about the meaning of that in just a moment. All right, so there's the overall parts of the rate law. All right. Here in your notes we have a key. Again, K is the rate constant. X is the order with respect to reactant A. Y is the order with respect to reactant B. Z, the order with respect to the catalyst. E, of course, is the catalyst. But right here, this is really important equation. I'm going to circle that. This equation right here you need to know. To get what is called the overall order of a reaction, we have to add up all the powers of the reactants and or the catalyst if it's there. So we just take X plus Y plus Z, and that will give us the overall order of the reaction. Very important to understand. Again, one more time, to get the overall order of the reaction, we add up the individual powers in the rate law expression. All right, so let's talk about the rate constant for a moment. These are some things, some points that you need to know about the rate constant. First of all, the rate constant is specific for a chemical reaction. The rate constant will change based on the chemical reaction or process that's going on, so it changes. K is not affected by concentration of the reactants, and it is independent of the initial concentrations. However, this next point is super important, so I'm going to actually circle that. K is affected by temperature. All right, that means that when we calculate a K value for a particular reaction, it is only as good as what the temperature of the reaction occurred at. So if you change the temperature in any way, you will alter the K value. All right, so you got to keep that in mind. K is also affected by the presence of a catalyst. If you add a catalyst, the K value changes. This next point is also really important. The units of K does have units, and those units are determined by the overall order of the reaction. So that's when you have to go back and you have to add up all of the powers in the rate law expression, add them all up, and the overall order is going to then determine what the units of K will be. All right, I will show you how to do that in part 2 of this lesson. The last one is really important too, so I'm going to circle that. The larger the K value, the faster the reaction will be. All right. So these three points, bulletin points that I circled, master, know very well. The other ones are important too, so have a pretty good general idea, but definitely those three that I circled. All right, let's talk about the order of a reaction and what that means exactly. Here are some 3 important bulletin points about the order of the reaction. First of all, the order of an individual, okay, the order of an individual reactant determines how concentration changes, affects the reaction rate at a given temperature. So what we're saying here is the order of the reaction and the order of an individual reactant. When you change the concentration, the order will determine how the rate is affected. All right, this will make more sense when we get into some problem solving in part 2 of this lesson. For now, just think that if the concentration changes, the order for that reactant, so in other words, we change the concentration for the reactant, the order of that reactant will determine the increase or decrease rate of the reaction. Okay. The overall order of the reaction is the sum of the powers of the individual reactants, which we talked about. That includes the catalyst as well. And this last one is important to keep note of, is that the order of the reaction can only be determined experimentally. You cannot derive it from a chemical equation or expression. Okay, what do we mean exactly by that? Okay, well, let's go back up to our rate law here. So here's our generic chemical equation. You cannot use this chemical equation to determine the rate law, right? The only way to determine the order is through experimental data. And I will show you in part 3 of this lesson how to use experimental data to solve for the orders of the chemical reaction. All right. Now, this does not hold true. This last point does not hold true if the equation, the chemical equation, is an elementary step. All right. So we'll explain to you what that means a little bit later on in our study of kinetics. For now, don't worry about the elementary step. Okay, just think in mind that if we're going to determine the order of a reaction, we have to do so through experimental means. All right. So that's it for part one. Just review your notes. Make sure that you understand what the rate law expression is, the parts of the rate law, understand the key factors of the rate constant, and what the order of a reaction does for the rate. Just remember that the order of the reaction determines let me rephrase that. The order of the reaction dictates what's going to happen to the rate of the reaction when we change the concentrations of the reactants. Okay? That's it. All right?